chi-square goodness of fit test. So in chapter 10, we discussed inference procedures for comparing proportions with two populations of treatments. What if we want to examine the distribution of one categorical variable in a population? For example, birth weights that are evenly distributed across days of a week. To answer this, we use something called the chi-square goodness of fit. Like our t-test and our z-test that we do, this also has a CDF in your calculator. So you'll see something that says chi-square. The symbol for chi-square is a symbol that looks like this. Chi-square. Don't ask me why, I don't know. Chi-square distributions are a family of distributions, kind of like the family of parabolas that we talked about in Algebra 2 and pre-calc. And they take on positive values and they're skewed right. Each particular distribution talks about degrees of freedom. The mean of a particular chi-square distribution is equal to the degrees of freedom. Each chi-square begins at 0, at the horizontal axis, increases to a peak, and then approaches the horizontal asymptotically, like we've seen in the past, and looks like a normal curve. So down below here, you'll see all these pictures of chi-square graphs. The one that's in black with a degree of freedom 1 is the only one that does not start at 0. That is a very rare case. You're probably not going to have to worry about that. When you're looking for your p-values in technology, you will be able to do the following. Oh, do you guys have that on yours, the technology part?
Yep.
Yeah. How come I don't have that on mine? That's weird. Oh, there it is. Sorry. So in your calculator, you'll do chi-square CDF, comma, whatever you get for chi-square, which I'm going to show you how to do shortly, comma, and I don't use 999, I use 99, because 99 standard deviations, really, come on. And then the number of degrees of freedom like in our t-test. As your degrees of freedom increase, you'll notice in the blue with the degree of freedom of 8, you get more and more like the normal curve. So the higher the degrees of freedom, the better off you are. Just like in all of our other tests that we do, there's a 4-step process. This is the null hypothesis, the alternative hypothesis. You're going to talk about all the different proportions that go along with whatever you're talking about, and you'll see that in the context of our problem. So that's what each of these P's are standing for, like the percentage of red cars we see in our society or something like that. And the alternative is that at least one of them is correct. And I'll show you again that in the context. When you're planning, we're going to talk about doing the chi-square goodness of fit test instead of the t-test, one sample, z, proportion, all that kind of stuff. You're going to talk about the random sample. The thing that's really different about this one is we talk about all counts are at least 5. That's very important. And then for independence, this is the one where we talk about the population being 10 times the sample size and things being independent. When we do our stuff in the math part of this, what you're going to do is you're going to find all the expected counts. Again, I'll show you this in the context of a problem. It'll make more sense. We're going to find the test statistic, which is the chi-square. We're going to figure out what does that mean as far as the p-value or the probability or the proportion of the area under the curve, that thing. And to find our chi-square, which is a new thing, this is how you do it formulaically. You take your observed value, you subtract off your expected value, you square that for each one. You'll see these are like numbers in a table. And then you divide that by the expected value. After you've done that, for each one, you add them all up. That's your chi-square. And again, I'll show you this in the context of the problem to make a lot more sense. Then we look at the density curve and find our p-value. And the conclusion is the same as we've done in all of our tests so far. And if it's less than alpha, we reject. If it's not, we fail to reject. Questions? Okay, so in our first example here, according to the 2000 census of U.S. residents 20 and older, okay, that's not really supposed to be 191%. I'm going to guess that it's supposed to be 19.1%. Are in their 20s, 21.5 in the 30s, 21.1 in their 40s, 15.5 in 50s, 22.8 in 60s and older. And kind of the cool thing in our class is we take this actual data off the Census Bureau, so this was accurate at the time it was done. And so then down below, we see that we're going to be talking about a table, and they have the age distributions and the percentages for U.S. residents 20 and older. Members of this sample were chosen by randomly dialing landline phone numbers. Remember, this was done in 2000, so people had landlines back then. Do these data provide convincing evidence that the age distribution who answer landline phones is not the same as the age distribution of all U.S. residents? So as we do this, we start off the same way as we have in the past. I'm going to start out with HO, and my HO is the age distribution of people who answer landlines is the same as the age distribution of U.S. residents. So what we're trying to say is, hey, what we see in the table, or what we see in the percentages at the U.S. Census Bureau, should be the same distribution as we see in our table. Our alternative then is that the age distribution of people who answer landlines is not the same as the age distribution of U.S. residents. So that's our beginning part, our statement. The next thing that we do is we talk about our planning. So we will do a chi-square goodness of fit test.
Should we write down chi-squared?
You could probably just write down the symbol if you want to, that's fine. And did they tell us an alpha?
No.
Oh, darn it. At alpha equal 0.05 then, let's just say it. It gets annoying after a while. We have a random sample of 1,048 U.S. residents. That's from the total on the far right. Since the population of the U.S. is greater than 10,480, or in other words, our population is greater than or equal to 10 times our sample, our data is independent, and we're going to check our counts to see that all of our expected values are more than or equal to 5. So expected count means take the percentage or proportion that they tell us, multiply it by our sample size, and see what happens. So for example, when they talked about the 20-year-olds, right? They talked about 19.1%. So I take 0.191 times 1,048, and I get 200.2.
Has to be more than 10.
Has to be more than 5. I take, what was the other one? 0.215, and I multiply that by 1,048, and that's equal to 225.3. I take, Yes, greater than or equal to. Yes. I take 0.211 times 1048, and that's equal to 221.1. So as you can see in this one, I mean, it's ridiculously large. We're not going to have any problems on any of these. Take 0.155 times 1048, and that's equal to 162.4. And I would go to the nearest tenth in each of these. And then I take 0.228, that's all the older people, looks like, times 1048, and that's 238.9. And what you're going to say with all this stuff is, since all counts are greater than or equal to 5, we can now proceed. Okay, so we've shown all the things that we need to show. I'll pause right there while you guys get cut up writing. So now we do the math part. This is the part that's kind of new to us, other than that blue and orange expected count thing. So here's where we find the chi-square, and here's how it works. So don't forget, your chi-square stuff is equal to the sum of all of your observed values minus your expected values squared divided by the expected value. And you add them all up. That's what's going on. So what does this mean for us? This means that I'm going to have, if I look back up in my table, way back up here, these are all of our counts, our observed counts. So over here, these counts are my observed. This is what I saw in my experiment or my sample. Okay, so don't forget that.